Thanks to all the organizers for allowing us to speak about our work and to everyone that is attending this afternoon or this morning, depending on where you are. We would like to tell you a bit about our recent work done in collaboration with Stephanie, Bernardo, and Dan that appeared partially in a recent paper and will appear also in another paper, hopefully this month. So the goal would be somehow to study the distance conjecture in the context of symmetric spaces and see what are the assumptions under which it is satisfied. And in doing so, we will introduce some kind of mathematical framework that will also allow us to be a bit more quantitative and to draw somehow a line in between the theories that may belong to the landscape versus the one that would be in the swampland. So let me start with a very general introduction. So we by now believe the swampland distance conjecture to hold. So this states that if we consider a moduli space parameterized by the vacuum expectation value of our massless fields in the theory, while going from a point in the bulk to a point at the boundary, which is at infinite geodesic distance away, we should expect an infinite tower of states to become massless exponentially in the geodesic distance. In particular, in the case with more than one modulus, it is very useful to think about this in terms of a convex hull. So we can associate to each tower its a scalar charge to mass ratio, which is essentially the logarithmic derivative of the mass of its particle as a function of the moduli. And what it turns out is that if along its limit we consider the leading tower that becomes massless, and we plot it on the tangent space to the modular space, these towers would arrange in a convex shape. In particular, if we look at the nature of these leading towers, the emergent string conjecture states that there should be only two qualitative different types. One kind of tower is dual to a Kaluza-Klein tower. So essentially, it would correspond to the compactification limit, or it would correspond to a tower of oscillation modes of a tensionless critical string. And in the first case, at least for BPS KK modes, the exponential rate of decay of the mass is expected to be of this form for a theory that lives in the dimension and for which n are the compactifying. While for a string tower, the corresponding exponential rate would just depend on the external dimension. And in particular, another thing that we learned from top down would be that for each direction on the modular space, the leading tower would always have an exponential decay alpha, which must be bigger or equal the one of a string tower. These are somehow things that are kind of understood. What we would like to do is try to prove some of them in the case of locally symmetric spaces, just from a group theory perspective. So a locally symmetric space would be is a Riemannian space with constant Riemann tensor. And from the typical characteristics that we ask for a modular space, so for example, to have infinite distance limits, we will focus on non-compact symmetric spaces that hence have a non-positive sectional curvature. This is a very nice framework because it can be studied just from group theory, as such spaces turn out to be diffeomorphic of coset spaces of this kind. So G would be the isometry group, or the connected component better of the isometry group of the manifold. And it's of reductive type, that is, it's a product of an abelian factor and then a semi-simple Lie group. K, it's its maximally compact subgroup, and it's the isotropy group that leaves a point on the manifold fixed. And then gamma, which will be very important for us, is a discrete subgroup of G, which in the string theory setups is the duality group that leaves the spectrum of states invariant. And then if we consider an element of such a coset G, this will in turn correspond to a choice of moduli. So just to give an example, if we consider, for example, the bosonic string on a torus, on a k-dimensional torus, this would be the structure of the moduli space where the abelian factor R is just related to the dilaton of the theory.
Veronica,
So, yes.
can I quickly ask? So this is a structure that we have always when we have 16 supercharges, but also in some non-supersymmetric models, it can appear. So your argument is going to work more generally than 16 supercharges, or you're having always 16 supercharges in the back?
So let's say, for us, we never assume any number of supercharges. Then, of course, we are making some assumption on the spectrum. Then, if the moduli survive all the kind of correction in the non-supersymmetric case and can still be called moduli, and the spectrum is still the one we would expect, then I would say it could fall in this classification. Of course, I mean, yeah, one has to be careful with this. Okay, so what we will do is start from this framework and then try to argue for the distance conjecture and the convex hull formulation. While in the following, we will assume the emergent string conjecture and the sharpened distance conjecture to hold, and try to see how all the machinery that we introduced in order to prove the first two parts will help us classify the various possibilities that we expect to be in the landscape. So let me start with the distance conjecture. So we can show that this holds under some assumptions. So we assume M to be locally symmetric, which allows us to fully describe the boundary of the space, and in particular also all the possible geodesics that go to the boundary. Then we assume compactifiability, as was introduced in this paper. So that is essentially the volume of a geodesic ball in our space grows no faster than an equivalently big ball in Euclidean space with the same radius. And finally, we assume a semi-complete spectrum of charges, where semi-complete will be defined properly afterwards, and the presence of one state that becomes massless at some point in the boundary. Then from compactifiability, it was argued in this paper that the states of the theory should transform in sums of irreducible representation of the duality group. And moreover, if we want our spectrum to be invariant under duality, and then by definition of the theory invariant under the maximally compact subgroup K, assuming that the mass has some analyticity property, we can expand it in powers of the charges, where these powers are essentially a schematic way of saying a quadratic contraction of Q by something that is invariant under both gamma and K. And then this expansion should start from the quadratic order by group theory properties and the assumption that there is one massless state. Then, given this, we can show that the Swampland distance conjecture holds for all the infinite distance limits and along all the possible geodesics that reach these points, and for any particle content, so independently on the representation that our particle lives in. Moreover, if we make a further assumption, that is that the mass the mass squared of the states is precisely quadratic in the charges. That is, we have some kind of BPS condition. One can also show that the convex hull formulation holds. And in particular, the convex hull of the theory, of the particle of the theory, is precisely the weight polytope of the particle representation. This helps us also be classifying a bit what are the possible convex hulls that arise. On top of this initial assumption, we have also to ask for the emergent string conjecture to be true, and also to have some values for the exponential rate of kk and string towers, which essentially would tell us about the length of the weights in which the theory, in which the particles transform. And then also, for simplicity, we will ask that the particles transform in a single irreducible representation that is labeled by its highest weight rho. And given this, as we will show more precisely later, it is possible to classify the effective field theories that satisfy all these properties. So they are somehow following our swampland constraints. And these theories will be labeled by their duality group, their particle representation, and also the external dimension in which they live, which is an output of our assumption. So we never have to specify it.
Can I ask something?
Yeah.
So just to make sure I understood. So to show the exponential behavior, did you need to assume also that the mass goes quadratically with the charges, or that was not necessary?
So let's say it can go quadratically or with a higher power, power of the charge. It doesn't need to be quadratic. The important thing is that it doesn't have any constant term or any linear term. But still, let's say if the quadratic term was to vanish and there was only a cubic term, this would still satisfy the distance conjecture.
And doesn't matter what is the function in particular. So you will always get exponential in the field distance.
Yes, yes,
because of the
as long as it's invariant under gamma, under the duality group, and under K. Yes.
So I will give details about this.
Yeah.
Okay. Thanks.
Okay, good. So then in this classification, it turns out that we find only a finite number of possible polytopes on which the particles will arrange. And in particular, for each kind of polytope, there is more than one theory whose particle will fit. So the dimension will not change, but there can be different duality groups and different duality and different representations that give the same polytope. Moreover, these theories come in families in a sense that will be better specified in the following, but essentially the information about many of them just comes from a few. And the largest of this family is built from the polytope of M theory on T8, which has a duality group E8, and the particles are in the 248 representation. This is still a finite classification, so we find a finite number of polytope. Usually, in many of the cases that we know for each polytope one kind of string, a string example, but not for all of them. So it is still like a nice question to see if the other theories are actually indeed in the landscape, or for some other reason they should belong to the swampland. So now, after this quick summary, let me start going towards like the more precise part of the presentation. So first of all, let me introduce what locally symmetric spaces are, but let me take a step back and assume, let me not focus on the duality quotient. So let me just talk first about the globally symmetric part of the space. And also, for concreteness, let me focus on the semi-simple part. So let me not talk about the abelian factors, which are introduced very easily and trivially without any problem. And then let me also focus just on a single factor, on a single Lie group. And then for the semi-simple case, in each factor, what I will say just follows through. What is important is that in these kind of spaces, the geometry is essentially given by group theory. So in particular, we will be interested in metric, geodesics, and boundaries. The metric on a symmetric space is just given by the Killing form on G in a unique way up to a constant. And then with this metric, geodesics are just exponential maps. So if we give an initial point on the manifold, which translates to an element of the group G, and an initial velocity on a tangent space, that is to say a vector on the algebra, the geodesic will take this form, where t can be taken to be an affine parameter if we properly normalize to 1 the initial velocity. All this class of geodesics will get to the boundary of this space, which is geodesically complete. And moreover, it turns out that there is always more than one geodesic in general that goes to the same point on the boundary. So then it is a natural way of defining the boundary through geodesic compactification. So what one does is to define an equivalence between the so-called asymptotic geodesics when these have a finite distance for infinite affine parameter. And then a point at infinity corresponds to a class under this equivalence relation of geodesics. Importantly, one can always choose the representative of such a class to be parameterized just by an element of the algebra, and in particular, a Cartan generator corresponding to a non-compact direction in the moduli space, where again we take it to normalize to 1. Another way of characterizing the boundary comes from noticing that points at infinity are left invariant by so-called parabolic subgroups, which essentially have the effect of shuffling between various geodesics belonging to the same equivalence class defined above. So then it is clear that each point of the boundary is uniquely determined by a choice of a parabolic subgroup and a choice of Cartan generator. So to make an example, in the upper half plane, so the quotient of SL2 over SO2, the point at infinity is fixed by upper triangular matrices and corresponds to a geodesic with this exponential of this Cartan generator. While the point, for example, tau equals 0 corresponds to lower triangular matrices and has just the same Cartan element up to a sign. Now, it can be shown that these two parabolic subgroups and these two Cartan generators are just related by an element of SO2. And it is a generic statement that there are classes of parabolics that are essentially mapped one into the other by K. And so we can choose one element of each one of these K conjugacy classes, which we call standard parabolic subgroup. Now, let's introduce back the discrete quotient by the group gamma. So, needless to say, the form of the gamma that we choose is very important to determine the structure of the boundary. So, for example, if we quotient the upper half plane by the usual form of SL2Z with the S transformation and the T transformation with periodicity 1, we have the standard fundamental domain given by this chimney. Now, if we were to choose another discrete subgroup where the T transformation has a periodicity of 2, we would have a different fundamental domain with a different structure of the boundary in which there are 2 inequivalent points that are not related by an element of gamma 2. Importantly, in both these examples, the final fundamental domain is non-compact, but it has finite volume, which means that gamma is arithmetic. This essentially is to say that it is commensurate to some kind of group of matrices whose components are just restricted to be over the integers instead of over the real, as in the usual case. In this case of arithmetic subgroup, the structure of the boundary is very similar as the one that we saw before in the case of the globally symmetric space. That is to say, points at the boundary are still labeled by a Cartan generator and a parabolic subgroup, where now the important information about the boundary is just contained in the rational part of the group. And in particular, everything holds up, of course, to the action of duality. So essentially, 2 sets that are that differ just by an element of the arithmetic subgroup are the same point at infinity. So for example, this means that in the usual SL2 case, if we were to consider the whole real line plus the point at infinity, just focusing on all the points that are associated to a rational parabolic subgroup, this would be mapped all under S or T transformation to the point at I infinity, which is in our fundamental domain. Other examples always have a finite number of equivalence classes, so a finite number of infinite distance points. So this happens in the SOKK cases where we always have one equivalence class of in our standard parabolic subgroup, or also in the heterotic theory on S1, for which this is the coset space part of the moduli space, where we have 2 equivalence classes, one corresponding to the E8 times C8 10-dimensional theories, and one to the compactification to the SO32 one. Since all the information about the boundary is contained in these rational elements that are dense over the reals, it is clear that only a dense set of geodesics reach the boundary, while the generic behavior is ergodic motion inside the fundamental domain. And moreover, one nice thing is that such parabolic subgroups always have a unipotent subgroup, and this let's say, is along the lines of what was already noticed in these papers, for which to each infinite distance limit we could associate a unipotent element.
Veronica, can I ask you a question?
Yes.
So since you bring that paper or those papers, the technology of mixed host structures also applies here in principle, no? So is it possible to pull back their arguments to this setup? Like this is like a special case of what they do?
So I would say this is so there are some cases in which so there is always an SL2 subgroup, like we can always along all the limits. The fact is that somehow we are assuming something different for the spectrum, which like we will say later what we will assume, because just so in some way, for instance, in these SL2 cases, we will need also the S transformation and not only the monodromy matrices to make the thing go through. I don't know if this.
Yes. Although I don't see why you couldn't try to do just with the generator, like they would do. But okay.
Yeah. So let's say there are cases in which you cannot. Spoiler for the following: you cannot build a whole tower just by acting with a monodromy. There would be some representations
of
the charges that don't allow this.
Okay, thanks.
Okay, so now we assumed that the duality group is arithmetic. Now, it seems to be fine because all the duality groups in string theory have this property. At the same time, it could also seem that we are cheating a bit and then we are taking this assumption a bit ad hoc. But actually, this is not the case because it can be shown to derive from compactifiability, that in turn would be a consequence of the fact that quantum gravity amplitudes should be finite. So compactifiability would mean that the volume of a geodesic ball of radius r in our locally symmetric space, for example, should grow not faster than the volume of a ball of the same geodesic radius in Euclidean space with the same dimension. How does this volume grow in case of symmetric spaces? In general, it has this form, so it has a power law in the rank of the group G, times an exponential factor in the radius with some, this norm of rho essentially is just the norm of some weight in our group. That is never vanishing because indeed it's a non-zero weight. So then this exponential behavior would in principle spoil this property, unless the biggest radius that we can fit in our fundamental domain is finite for any reason. So then, if we ask compactifiability, this means that at least in the cases that are not of rank 1, so they are not SO1K or SU1K for technical reasons, this means that M, in the end, would have to have finite volume, which in turn implies that gamma is arithmetic. And moreover, asking about compactifiability gives another bonus, that is that the spectrum should transform, as said already before, in representations under gamma. That thanks to these math results allows us to extend the representation to be actually a full representation over the full group G. So this was a very quick summary of the math part. Hopefully it was clear. And now Marianna will take over and just explain you how we use this machinery to prove the distance conjecture and then say something about the possible representations.
Mariana, you're muted.
Yeah, sorry. Well, I go on. I thank the organizers as well. So as Veronica said, the spectrum is the space of states that are in a representation of G. So now we know that it's not that a representation of gamma extends to a representation of G. And these representations we will label by the highest weight that we call rho. Now the representation acts on Rn, and there's a lattice that is Cn. And so the simplest example, let's take 011. So compactification of the bosonic string in a circle and forget about the dilaton. So this lattice would be momentum unwinding. And then we're not assuming completeness, so we're not assuming that all this lattice is populated, but we're assuming that there is some sublattice that is populated, that is defined by some condition, and some condition that is invariant under gamma. And we will need to assume a little bit more than this, which is the semi-completeness, and we will see what it is. No, sorry. Let's see how we are. Okay. So we assume the semi-completeness, and then we also assume that at least one state becomes massless at the boundary. And with this, we can prove the Swampland distance conjecture. So now, coming to the mass of the states. So the mass of the states has to be an invariant function of the charges and the moduli, and depends on the representation. So let me do again the example of 011 or in general OKK. So the charges are momentum unwinding now in the different directions, and the masses have this form in terms of this generalized metric that has the metric and the B field. And that one can write this generalized metric, one can write in terms of B-Elvine, the B-Elvine of the metric, and the B field, and this is an element of G over K. Now this...
Sorry, can
yes.
I ask a question?
Yes.
Have you tried to show somehow this semi-completeness rather than assuming it? Like, for example,
Yes.
I mean, I agree you cannot just use the monodromies of a given limit, but using the monodromies of the other limits and taking into account that the divisors intersect and different things.
So it might be that the semi-completeness is too strong of an assumption and we can relax it, but we don't know how to relax it so let me maybe when I will define what semi-completeness is later. But well, we'll see. We can discuss that again when I define semi-completeness. Okay, so now in general, if we call two screens, so if we call this this sort of dressed charge vector, so using this B-Elvine that depends on the moduli, we create this vector P that depends on the charges and on the moduli. Now, the mass in general, the mass square, should be some function of this P, and it should be some invariant function. And in general, we can expand it in powers.
Can I ask you a question? Could there be higher order invariance of the charges?
Yeah. So yeah, constant plus P squared plus order P to the 4, and I could have all sorts of higher order invariance. So depending on the group and the representation, one can have more invariance. So, I mean, this will be okay for the Swampland distance conjecture. Then we will drop it for the rest, but for the Swampland, as far as the Swampland distance conjecture, this could have higher orders. Now, if we're assuming that one...
sorry to interrupt. The M could represent tension or anything. You don't really mean particles, correct?
So we've done this for particles. In principle, this could be done also for brains, and we did a little bit. So it will be the same. I mean, this part will be morally the same. It's just that then the story about the convex hull and everything becomes much more complicated. So I mean, so this could be particles or brains, and this will be the tension. Yes.
Okay, and are there cases where you don't have a quadratic term or always starts with quadratic term? I mean, supersymmetric case predicts quadratic term only by BPS conditions, but are there cases where you could not have had a quadratic term only?
Yeah, I mean, I'm sure there is, but I don't know. I mean, I don't know, in E7 with the 56 representation, that's not what happens, but in principle, one could have a
Daniel wants to say something.
But, sorry?
Daniel is saying something?
Yeah, I could add, I think they have to be invariant polynomials of K. So the first two terms are constant and quadratic, and then they can be higher terms, but they'd have to be, there can't be a linear term.
Right, so there always is a quadratic term like Casimir, right?
There's always a quadratic term, yeah. You could.
So this is consistent with the supersymmetric case always.
And then in the supersymmetric, there'll then be nothing higher, but in principle, there could be higher things, yeah.
Okay, thanks.
Yeah, sorry. Okay, good. So there's always a quadratic term, yeah, which is, yeah, so the Casimir of the representation. So so now along geodesics, so we're interested in these geodesics that go to the boundary. Then geodesics have this form, the ones that go to the boundary, that were the ones we are interested in. So then this P that depends on the moduli in particular, so the moduli will depend on this distance, this proper distance along the geodesic. And again, let me do OKK, which is nice and simple, or where one can see how this works. So this E to the H, so the Cartan is labeled by, so one can grow. So for example, with this, if this lambda1 is non-zero and the others are 0, then one is growing one radius of the R1 of the compactification of the torus. And the if the others are non-zero, if all of them are non-zero, then one is growing all the radii. And so so basically this and the charges are the winding and the momentum and the winding charges. So in short, one can write it this way. And again, remember we want for T to be the proper distance, then this has to be properly normalized, can normalize to 1. So now in general, so this was for OKK. In general, what happens is that this we have the charges are decomposed into, so the Cartan decomposes into weight spaces, and this P has this exponential form in e to the minus t, and then what we have here is the weight of the representation and the element of the Cartan. So let me give you an example. If we take the Cartan, if we row just R1 of the torus, then the charge is, so, well, if we row, so let me say one more thing before that. So, and then if we want to look at the fastest tower, then we have to see all the weights of the representation and see for which this is maximum. And this will depend on which Cartan we are. So whether we are growing one radius or many radii. So this maximum weight will depend on which Cartan we choose. So for example, now choose a Cartan that grows, that takes the radius of the first circle to infinity. Then the charge, the fastest tower is given by the tower of momentum along that direction. And then the corresponding weight is then it's 1, 0, 0, 0. If it's the other way around with the lambda, so I'm taking lambda to be positive. If it's the other way around, then I can take plus lambda. I take plus lambda minus lambda, then I will have winding and has a charge equals -1. A weight, sorry, equals -1. So now let me assume that there are no higher orders. Again, for the Sonnenbland distance conjecture is fine, but for what we're going to do now, which is this convex hull formulation, then we need to assume that there are no higher order terms. So let's do the example of the 3 of SU3. And one can draw this alpha hull that was drawn in this paper, which are the projections. So I mean, in this paper it was drawn as a charge to mass ratio with derivatives of the charge to mass ratio. Here we see that this alpha hull is just a projection of the Cartan on a given weight. So, or here, if the Cartan is within, sorry, if the Cartan is in this direction, then the projection that is going to be largest is the one given by this weight. So if the Cartan is in this direction, the projection that is going to be larger is the one given by this weight, and etc. So this omega star, which is the weight of the fastest tower, depends on how we choose a Cartan. So it jumps from here to here once we pass this point, for this Cartan. So was noticed in this paper, these distances are always larger than the distance to the convex hull. So the convex hull, this convex hull that is between these vertices, between the maximal hull that is contained in this voice, in this alpha hull. And what we notice is that this convex hull is just the wild polytope or the weight polytope, the weight is called either way, of the 3 representation. So just using this group theory thing, then we get a lot of mileage and we can prove the Sonnenbland distance conjecture, and then we can do this classification that I will tell you about. Now, the extrema of alpha are at the vertices, which are local maxima, or in the middle of the facets, which are local minima. And the absolute minimum is not hard to see that they only happen in the middle of facets, but facets which are codimension 1, so sort of the largest facets. If this is an absolute minimum, this will be alpha string, and if it's a local maximum, it's alpha kk, and a local minimum can be either kk or string, depending on the dimensionality of the facet. And now the distances to facets, which are the alphas, can be computed purely using the Cartan matrix and linking levels of the representation. So this is not what we did in the paper that we posted, but in the upcoming paper, we show how to do this. Now, so the proof of the Swampland distance conjecture, so we showed that the mass of the states goes like this, but assuming that there is one state that becomes massless. Now, why do we have a whole tower? And here there are two things that come. So one is what we already saw. This is the lattice L, like Z to the N. So one thing is that these are the weight spaces, and because the boundaries, because the boundaries are associated to rational parabolics, this is a rational line. So if I go one step before, so I don't spoil. So these weight spaces are a rational line here. So they always intersect the lattice in an infinite number of points. Now, if we assume completeness, this will be all, and we will say then we have an infinite number of massless states, of states that become massless. But we haven't assumed completeness. We have assumed this semi-completeness, which is a little bit weaker, which says that for any W, for any weight in the vertices of the wild polytope, the intersection of these weight spaces with the lattice is the same as with the lattice, the generic lattice, Cn, is the same as the intersection of the weight spaces with the lattice that is populated. So this is what we call semi-completeness. And there might be a better way. So this is a sufficient assumption once we go to this point, and this point is very general. So this point uses rational parabolics, which is math. So this point is very general. So now we wanted to see whether we could relax completeness, and yeah, we have this condition that is sort of semi-completeness, in the sense that our lattice could be given by some invariant condition that is stronger than the whole Cn, like the whole the largest lattice, let's say, that is invariant under the group.
So sorry, Mariana, can I quickly ask? So usually so what you're calling completeness or semi-completeness is more like what we usually call BPS completeness.
Yeah, exactly. Yes. Yes.
Okay.
Yeah. Within, I mean, it's like a BPS condition,
okay.
But I mean, it could be, in principle, it could be more general than a BPS condition, but it's sort of a BPS type condition. Yes.
But it's different from the weakest form of completeness, which is just the state exists, but I don't know what the mass is.
Yeah.
Yeah, so maybe if I can ask again, so because this is one of the tricky points, no, to show the distance conjecture, like also with the monodromies, no, how to show you have the infinite tower and not only a finite number of populated BPS states. So something we tried was to try to use other monodromies from other intersection loci. I don't know if here you have, I mean, in our case we didn't have a global picture of the moduli space. Maybe here, so you have the symmetric moduli spaces and the full duality group. I wonder if you can make this argument stronger, no? Like try to use part of like the full duality group to show, no, that you will have this BPS completeness. There's another paper by Eran, there's another way, but it's more like using black hole arguments to show also for the existence, no, of the states.
No, I completely agree that it would be very nice to, and maybe we don't need this semi-completeness, and maybe we can do something similar to what's done with these Hodge structures, that you just need locally symmetric spaces at the cusps. As Veronica said, so here we're not assuming this goes for any representation, while in this n equals to 2 theories, then you have a particular representations that appear, or depending on the, we can discuss later. It's going too much in detail, but your question is very relevant. I wish, maybe one can have one can prove this in some way. And the important point is, everything is important, but this holds for any infinite distance limit, because as Veronica said, any infinite distance limit is associated to some rational parabolic, so we have this rational thing. these are rational, so they intersect the lattice in an infinite number of points. And so what's different is what are the cartons that one is taking, and a choice of carton then makes this decomposition into white spaces. But whatever the cartons are, this will always be irrational associated. These lines will always be irrational. Now, this classification of allowed IFTs, maybe I will have to rush. So what do we call by allowed IFTs? So it's the set of groups, representations, and external dimension, though the external dimension will be an output. So the set is actually of groups and representations, and then that will only happen in a given dimension, such that these distances are either the one of a string emergent string tower or the KK towers. And then it happens that this n is the dimension of the facet plus 1. So assuming particles in a single irreducible representation, so this classification that will appear assumes particles in a single irreducible representation. It becomes much more complicated if we don't assume that, but it's a generalization that one could in principle study. And we also assume the split form SOKK. Though this, we have an idea how to relax. We haven't done it yet, and we won't do it for this paper probably. But here we assume the split form. So we have of the order of 20 allowed groups, and here I'm counting like SOKK times R. So SOKK by itself doesn't satisfy this, but you need to put the dilaton direction in order to have this alpha string. So, and I'm counting this for all the case as a single group. And for a given group, there's usually a single representation allowed, or at most two representation allowed. Modular scaling of the highest weight, I will tell you in a minute what it is. And the dimension is given, it's an output. So this is very nice. It's very restrictive, actually, having this. So this modular rescaling of the highest weight, what it is so it's not hard to see that the conditions are invariant under rescalings of roots and highest weight in this form. So you rescale the weights, so you increase the representation because you rescale the highest weight, and then you decrease the roots. So the solutions are characterized by a minimum representation, because one cannot decrease. So in principle, this k, I could put this the other way around, or say that k is a rational number, but there's a minimum representation such that all the vertices of the polytope are weights of that representation. So there's a row minimum, or analogously a maximum long root. And well, I'll say this with less detail in the conclusions. Let me jump to the conclusions in view of time. Or let me say this. So the families are, so these come in families, and it depend on, the families depend on what is the norm of the long root, the maximal long root. And the families with the long root square equals 2 this is unique, is biggest, and we know the string realization of many, and it comes from M theory on E8. M theory, sorry, comes from E8, which is M theory on T8. And then there are smaller roots. So we know some string realizations, and larger roots, and we do not they do not seem to have a string realization, but maybe it's a string realization that not with the standard rules, at least not in the orbifold type of thing. Okay, let me conclude. So we gave a unified description of the boundary of locally symmetric spaces. There's a finite number of points on the boundary up to the action of gamma. So this picture of the moduli space with a finite number of cusps is correct for moduli spaces which are locally symmetric. For any boundary point, there are canonical geodesics that reach that point that are of this form, where if T is the proper distance, then the H, so when H is normalized to 1, then T is the proper distance. Now, then given a spectrum, which is in some representation of gamma or some representation of Xi, and has a given highest weight, and weights in general weights W, assuming one state becomes massless at the boundary, we could show that the mass has this form. And then, well, this story about the fastest tower is the weight where this inner product is maximal, the alpha are the extrema, and these extrema are this polytope is the wild polytope of the representation, and then you can compute this alpha, so this distance is using just group theory. Now, requiring the distances to be of the form alpha string or alpha kk, and assuming the split form and the particles in a single representation, we got the full set of theories with a moduli space G, allowed representation for particles, which in general is most of the cases is unique, or at most there are 2 allowed representations, and there is an output of what's the dimension where they can arise. And they come in families that are generated by some seed, and the largest family is a family that comes from E8, which corresponds to M theory on T8. So now the question, so this question mark should come afterwards. So in this picture of landscape and swampland, suppose that this alpha string and alpha kk are my constraints, then what happens? So the question is, are we exactly do we fall exactly in the landscape? Do we miss some things that are in the landscape? Do we fall partly in the landscape and partly in the swampland? And this is a very interesting open question. And so one thing, well, I didn't talk about this, I didn't talk about too much about this rho being rho minimum, but this is not enough. Then we have to assume, because of this rescaling, we have to assume that the particles are in the representation given by this minimum allowed rho. Because we know that if this is not the case, then for sure we fall. There are some things which are in the swampland. Okay, so thank you.